energy networks, but that's absolutely fine. So the aim of this, I'm really glad to see so many people here. The aim of this is to try and do a little bit across the different hubs. So there's 5 Supergen hubs. This is always the test. So there's energy networks, energy storage, super solar, bioenergy, and offshore renewable energy. And so the aim is to try and get people to understand a little bit more about what's going on across the different hubs. So what we're doing today is a quick kind of research showcase, and we're hoping that this will be the first of many of these. We've got a few other interested speakers lined up as well. And so each speaker is just going to do a very quick 5-minute presentation, even less, and then a little opportunity for questions, just so that everybody can find out more about what's going on in all the different hubs, and maybe you can see some connections and think, oh, that's interesting, I've got an idea, maybe I'll get in touch with that person. Just so you all know, we are recording it. So the only thing that gets recorded is the main speaker. Right now that's me, and then the screen, and then the person talking. So we'd ask that you keep yourself muted if possible. If not, we might mute you. So don't be annoyed if you discover that you've been muted. That's just to keep the background noise as low as possible while this is happening. And obviously, if you're a speaker, when it comes to your turn, just share your screen. You've got the running order. Just share your screen, and then that will take over. The only other thing I want to say before we kick things off, the next webinar session that we've got organized, we will send it out through the same channels that you received this. So if you received the last one, you should see the next one. But that's actually going to be on the 2nd of July. And it's not a researchy one. That one is about well-being and working from home. So it's about what you can do to try and look after yourself, particularly during this, to make sure that you have obviously it's a very stressful time and a very different way of working, so it's giving you some of the skills to help you out with that. I know it's something that I'm definitely going to be signing up for. So that's going to be on Thursday the 2nd of July, 10:30 till 11:30. So we'll send out the links and everything to that after this, and you should get that through the exact same mailing lists, etc., that you got this through. So that's everything I wanted to say. I don't think there's anything that I've missed. I'm not seeing any of the other hub organizers waving at me desperately. So on that basis, I think we'll jump into
Robin,
the first presentation. Oh yes, Richard, please.
I was just going to say format for questions would be useful.
Oh yes, excellent. So if you do have a question, we obviously won't have a lot of time for lots of questions. Best thing to do is to put it into the chat window and maybe just put a capital Q at the start, and then we can find out what's, we should be able to spot those easily. And then also, if we don't have time to go through all the questions, then the speakers might be able to answer them directly in the chat window as well afterwards. So if you do have questions coming up, please just drop them into the chat. Oh, and also just a general thing, if you have any other ideas of what it would be nice to do, cross-hub, this kind of thing, if you've got any ideas of, oh, it'd be nice to have a webinar on this or something like that, just drop those ideas into the chat as well, and we'll save the chat afterwards. Don't worry if we don't mention that we've seen it, we will see it, we'll read it, and we'll have a look at those ideas as well. So that's everything from me. I'm going to jump straight into our first speaker. Our first speaker is Katie Shanks, and this is an Energy Networks one, so over to you.
Yep.
You should be able to just share.
And yep, just sharing this. So here. Yep, does everybody see that all right?
Perfect.
Perfect. Okay, yep, my name is Katie Shanks. I'm a postdoctoral researcher at the University of Exeter. The research I'm going to be describing today is the Energy Independent Farms project we have, which is funded by ERDF. So specifically, we're looking at dairy farms, and specifically, we're trying to get them off grid so that any energy that they're generating from renewables is being used on site, so it's less strain on the grid. So the demand profiles of the farm is shown in the top right figure, and then the biogas, because they're wanting to try and start selling the biogas that they're producing from their slurry pits as methane to make profit as well. That's shown in the bottom graph there as well. So the biogas processing is actually quite a high demand for the farm, so it's almost as much as the farm demand. And they're already at their capacity for the grid. So hence this idea of bringing in renewables to supply that energy on demand and take the strain off the grid without having to update it or anything like that as well. So just to give an idea of the megawatt hours renewable generation and the costs of those renewable energies, these two tables kind of give a some rough numbers of the megawatt hours generated per year and the capital cost of those increasing wind and increasing solar. So the blue is the kilowatts of wind, and the column yellow is the kilowatts of solar. And obviously you can get higher, and the bold numbers are what would actually meet the demand if you could take all of that energy. So not even taking into account the energy storage yet, those would be the minimum. But of course, with energy storage, you want your storage capacity to be lowest. So hence you want a combination of solar and wind to bring down the actual the capacity required at any one time. So that's just showing that. In terms of actual energy storage, so we're looking at trying to use methane, the methane that's produced, to supply the missing energy. But in this case, the methane can be sold for a profit. So we actually don't want to use too much of the methane. So we have this kind of balance that we're trying to go for. And the table there shows an idea of how much the lost revenue would be if we used all of the biogas to meet the demand and minimize that by installing RE. And then we compare kind of, so the graph below shows if you use all of the methane every year to supply all demand, that becomes a large cost, even bigger than buying lots of batteries, which is usually seen as the most expensive form of energy storage. But if you can reduce that with RE, then you can minimize the methane, and it becomes a lot more affordable that way until we can maybe buy more renewables. So hence we're kind of approaching this idea as a staged project. So install one amount of RE, and then later, once there's more money generated from the selling of methane, you can maybe upgrade your RE and become more energy independent, and hence make more profit. So that's the overview of our project, basically. Yeah, and questions are welcome. And the graph there just shows the, with that example I gave, 100 kilowatts of solar and 80 kilowatts of wind, the average power supply, and hence the power demand as well from the farm and battery as well.
Brilliant, thanks so much. So I can't see anything in the column, so I'm going to chip in because I get that right. So just how far through the project are you?
We are at the stage where we'll be starting to, we're going to be installing some wind, and there's already solar installed. So okay,
excellent. Yeah, so coming along then. Okay, brilliant. Yeah. Thanks very much. We might get some more questions coming up later, but that's really interesting to see. Thank you very much. So obviously, in the interest of time, we'll move straight on to the next one. The next one is Agota Makute. Sorry if I pronounced your name badly, but you've already taken over. You're muted currently, so
yes,
unmute yourself.
Working on
Perfect.
it. Working on it.
Excellent. Thanks very much. So over to you. And this one looks like an offshore renewable energy hub one.
Yeah, so my name is Agota Matskute. I'm PhD at the University of Hull, and I'm working on the structural response of monopile-supported offshore wind turbines and how waves tickle them. So structural engineering 101, resonance is bad. Resonance causes a lot of damage to the structure and can lead to its failure. That's why designing offshore wind turbines, we are trying to avoid the frequencies that might lead to resonance. The ones to avoid are the one revolution of the rotor, the blades passing the tower, each of the three blades here at the higher end of the spectrum, and the frequency of wind and frequency of the waves. That's why the monopile-supported offshore wind turbines are normally designed so that their natural frequency falls in this middle green range. The problem is that waves are a broad-banded frequency. That's why the higher end of the spectrum might overlap with the natural frequency of the turbines, causing nonlinear resonant phenomena, which causes these huge amplifications in the response with slow decay. To give a little feel of this, I tried to find some video. This is not specifically offshore wind turbine, but it should give a feel. These huge amplifications and slow decay, which causes a lot of damage to the structure, up to 20% higher fatigue and extreme loads. So we really want to model these numerically, predict them, and account for the damage that they cause. Numerical modeling of wave loads on offshore structures involves modeling wave kinematics at the location of the structure, accelerations and velocities, and using hydrodynamic loading models to input these kinematics as well as characteristics of the structure to get the forcing and response. So to model ringing, we can use linear second order or fully nonlinear wave kinematics. They're in increasing complexity, that's why increasing computational time. For hydrodynamic loading models for slender structures that monopiles supported offshore wind turbines are, Morrison equation is most common, but there's also a bit more advanced Rainey and Effen-Wu theories. And in the literature, it is seen that regardless of the hydrodynamic loading model, with linear wave kinematics, ringing is omitted, but with fully nonlinear wave kinematics, it is captured regardless of the hydrodynamic loading model. So why don't we just use the fully nonlinear wave kinematics? Because they are very computationally heavy. The intermediate second order wave kinematics, which are okay to be used in the industry, were seen to not capture ringing if Morrison equation was used. But I couldn't find any literature discussing second order wave kinematics with the more advanced hydrodynamic loading models. So that's one of my objectives in my PhD research. And what I found was that, in fact, the amplification seen with fully nonlinear wave kinematics were not captured by the second order wave kinematics, regardless of the hydrodynamic loading model. So unfortunately, we can't optimize and say just use the second order wave kinematics, because in intermediate water depth, the nonlinearities in wave kinematics matter so much more. So I really suggest using fully nonlinear wave kinematics to capture these amplifications, this wave-induced resonance on monopile-supported offshore wind turbines. And what's next, what I'm working on now, is that scour occurring in the first generation monopiles, the first monopiles that were installed in the sea, or the future, the larger monopiles that we place in the sea, they naturally have lower natural frequency, so that may increase the range of waves that could trigger ringing. So the more commonly occurring sea states might trigger these amplifications. So I'm working on quantifying this increased response and its effect on the lifetime fatigue. So thank you very much, and I'm hoping for some questions.
No, brilliant. No, that's really interesting. So there is a question in the chat, which is basically saying, you've done a lot obviously on the modeling, so does that also translate through into a kind of age reduction, so how that maps through into the stress on the monopile?
Yeah, I'm now trying to work on quantifying the lifetime fatigue, but the stuff that I've done already was mostly on 1 hour nonlinear sea states, and that was seen, the nonlinear amplifications were seen to cause about up to 30% more fatigue. So since these very nonlinear sea states don't occur for the whole of the lifetime, it will not directly transform into 30% less lifetime, but accounting for scour, for example, might increase the probability of sea states that trigger it. So yeah, I'm still working.
So there is another question, but I'm going to let you answer that one in the chat, because I think that one's going to get into a bit of the detail around that scour stuff, which is a word I don't even know what that means. But thank you very much. It's a really interesting talk. We'll have to move on to the next one. So next up we have I'm gonna assume, is it Jorge or Dovas?
Yeah, that's great. That's great pronunciation. Thank you.
Excellent. Right. Which one? I'll pass over to you, and you can speak, and I'll stop.
Yeah. Let me see. You can see the screen right now?
Yes.
Okay. Perfect. So hello everyone. Good morning. I'm Jorge Lopez Ordovas. I'm from Aston University, and I'm going to present as part of the Supergen, the bioenergy hub of all of them we can have. So I'm at Aston University. I'm at the Energy and Bioproducts Research Institute, and I'm under supervision of Katie Chung and Tony Bridgewater. I'm a PhD student. And I'm going to explain a bit of the construction of a model for the design of a rotary kiln for a slow pyrolysis of biomass, and it's part of the Green Carbon Project. It's a European project that, well, I don't have time about that right now. So I want to start explaining what's pyrolysis. And pyrolysis is just increasing the temperature of a feedstock to produce these three products: char, pyrolysis oil, and gas. So the feedstock normally is waste biomass to avoid using some soil using soil that can be used for food. The objective is to use the soil to plant food, and then those residues from harvesting and other residues from biomass, using it for pyrolysis to produce gas, which provides heat and electricity, pyrolysis oil, which is used for the production of chemicals and for the production of heat and electricity, and then char, that can be used for carbon sequestration, soil amendment, and energy production. So the system that I'm designing on my PhD is a rotary kiln. It's the cylindrical shell which is rotating. We put the biomass from this side, and then on this part we obtain char, and we obtain the pyrolysis oil and the gas. So the direction is this. It's slightly tilted to the surface, so this shadow is actually real. It's quite a complex system. We have three different factors to take into account. We have to consider the bed of solids because they behave in a different way. That normally we have to consider how they evolve, how they behave under the rotation, and how homogeneous the product and the solids inside the feedstock, inside the reactor can be. Then we have to consider the heat transfer is a very important part in pyrolysis. Some other reactors are a bit restrained by heat transfer, so it's important that the kiln that we're designing is actually working and as homogeneous as possible, avoiding any kind of temperature gradients inside. And finally, pyrolysis is a very complex process because the kinetics are not clear. The pyrolysis oil combines many different substances, and it's impossible to have the kinetics for all of them. So the idea is to have a feeding rate, feedstock type, a moisture content at a target temperature to put inside the model. And then the model will do all the calculations and will give the length, the diameter of the reactor, the kiln angle, but also the product yields, the product flows, and the conversion, and some processing parameters such as rotational speed or temperature profile. Temperature profile of all the reactor, the wall, and the solids inside. Oh, sorry. And just a bit of overview, what I'm trying to do to model this reactor is dividing this reactor into slices. So as we see on different colors here, and on each of the slices, we're implementing the same algorithm. So we are just, we create all the slices, we put the same algorithm, and we use the output from one slice into the next one. And in that way, it's easier because the systems are smaller and they are more real, and it's easier to model. And that's all I wanted to tell from myself. And if there is any questions or so, feel free to contact me or ask right now. Thank you very much.
Excellent, thank you very much. One quick one from me because I can't see any in the chat. So again, I get the opportunity. Are you building this as a physical thing as well, or are you comparing your model to a physical one?
No. Well, actually, I'm now finishing my PhD. I'm handling in a week, so it's a very
good luck.
Yeah, thank you. No, it's quite fun time right now. No, it's just a computer model, but it's a model that it's a program that aims to design a reactor no matter what the inputs are. So it's not it cannot be very complex, but at the same time it has to be consistent to get a PhD done.
Of course, excellent. Thank you very much for your talk. Next up, we have Alberto Bolzoni. And this is an energy storage talk. So take it away.
Yeah, so good morning, everyone. My name is Alberto Bolzoni from the University of Manchester. I'm a postdoctoral researcher. And in this presentation, I will speak about grid-scale battery storage. So obviously, all of us, let me see, we know about electrochemical battery storage, and it's a very mature technology. It has been studied in labs and in small-scale systems for a while, and in a real market scenario, because all of us, we see that most of the energy actually produced comes from traditional sources, and the more we integrate renewables into the system, the more the role of energy storage becomes important. So we need to evaluate and to analyze how it is possible to make higher profits from electrical storage systems. We don't know the answer yet, but we think we know the tool in order to make it. And the tool is, as we are dealing with,
Am I the only one who's lost audio?
No, all of us, I think.
Okay. Alberto, if you can hear, we can't hear you.
He looks like he's frozen on the screen as well.
His pointer's moving.
Oh.
Okay. Well, what we'll do, and we'll move on to the next talk, and hopefully we'll be able to get Alberto back in a bit, and we'll do his just out of order. Okay. So next up, we've got Tudor David. Would you like to take over, and then maybe Alberto, if you can hear, if you leave and come back. Excellent. Let's stop that one.
Hello, can you hear me?
Yes.
Yeah.
Yes. Brilliant. You take it away.
Okay, so hello, my name is Tudor David, and I'm going to present work we've been performing on the forecasting of OPV performance and degradation using machine learning. How do we go to next slide?
Should just be a click.
Can't get it to next slide.
Have you got your full screen in front of you?
Yes, it's gone to full screen, but it's not going to next one.
Left, right buttons, spacebar, any of those? Nope.
No, none of them. I don't know what to do.
Go out a full screen and see if you can just do it through. Is it in a PowerPoint or was it a
PDF? PowerPoint.
If you escape out of the full screen, you can just do it from there if you like, or you can try
Okay, do it from here. Yeah. So what we've done is using machine learning to predict OPV performance and degradation. So we apply an MLP algorithm and it's trained on a period of 2 weeks of diurnal climatic conditions and corresponding OPV parameters. The algorithm is then applied to unseen days of climatic data in order to predict diurnal variation in these performance parameters. And here we can see the actual and predicted variation in the performance parameters over the course of a day. So then we can then use this information to calculate the energy output, and we compare this on a cloudy and sunny day. So we see this on the 5th of the 9th is a sunny day, and the 26th of the 8th is a cloudy day. And we see we can accurately predict the energy output. And then when we sum all of these energy outputs over the course of the whole test, we can predict the energy output with a 20.9% error. However, in order to be able to predict and forecast the outdoor performance of OPV modules more fully, we also need to be able to understand both the performance of the devices as a function of the daily weather conditions and also the degradation of the modules. So in order to model the degradation state, we have considered the total exposure of the modules to different climatic conditions, as well as the instantaneous daily weather conditions. So this can be considered analogous to the dose of each climatic condition. So the graph shown here illustrates how different climatic conditions can accumulate over time, despite the instantaneous values decreasing or remaining relatively stable. So the degradation of the modules is analysed by taking the PC at 250 milliwatt per centimetre squared over the course of 5 months. And the degradation is averaged over the 10 modules being tested. So this shows the predicted time-dependent degradation based on the exposure to environmental conditions. And the model employed here uses both the cumulative and instantaneous climatic conditions. So therefore, this allows us to know the forecasted state of the modules based on the level of degradation up to 6 months into the future, and is achieved with only 2 weeks of training data. So this significantly reduces the time required to test the modules, and therefore potentially provides a means of assessing technologies in a much reduced time frame. So then finally, we show how we can predict the degradation over the course of 5 months using a combination of methods. So the degradation of the modules is forecasted initially in 2 different ways. Firstly, using the MLP model, which considers the diurnal variation in the climatic conditions, and a model developed which predicts the daily yield variation based solely on the degradation state of the modules, determined from linear regression and considering the cumulative exposure to the different climatic conditions. And then what we do is finally, the results of these 2 methods is convoluted such that the effect of the degradation is included in the prediction made by the MLP algorithm. When this is performed, the percentage error is reduced to 4.1% as compared to 20.9% using only the MLP and 15.2% using only the degradation prediction and the initial state of the modules. Therefore, this provides a means of accurately predicting the stability and power output of the modules over a period of 5 months based on only 2 weeks of training data. So in conclusion, we have shown how ML techniques can be applied to understand and predict the operation of OPVs in real-world conditions, as well as predict the degradation rates of these modules based on the cumulative exposure to different climatic conditions. So I'd like to acknowledge everyone in my group, and thank you very much for listening.
Brilliant. That sounds like magic, the way the errors seem to disappear at the end. So we have a question from Richard saying, what's the predicted lifetime degradation? So can you map that out, I guess, further into the future? You're talking about a 5-month lifespan.
Yeah, so
prediction.
I think the error will gradually get larger and larger the further we take it, but we haven't tried going much further at this point, but that is the plan, is that hopefully that we can just take any forecasted weather, well, with the diurnal variation, that we take any weather forecast and we apply the model and see the output. With the degradation rate, it should be quite simple because it's just a matter of extrapolating out, and if you just plot in at any time. So if you're happy for the error to get larger, then you could just take this as far as you wanted to, potentially. It's just a matter of improving the algorithm, basically just to get the error as far down as possible.
Okay, excellent. Thank you very much for your talk. We're going to try Alberto again, if you're there, if you'd like to take over the screen share.
Can you hear me now? Yeah.
Yes. Okay. Yes, I can hear you.
So yeah, I was saying I'm Alberto Bolzoni from University of Manchester, and my research deals with grid-scale battery storage. And in particular, we are working on the evaluation of the battery storage profitability in real market scenarios. So in order to analyze how grid-scale battery units operate in real systems, we developed a setup which is constituted by a large-scale storage device. So it's a 240 kVA system and 180 kilowatt hour, which is installed at the University of Manchester, and it is physically interfaced to a RTDS network simulator for real-time simulations. So basically, the system here is a big, large-scale hardware-in-the-loop setup where it is possible to interface both physical units and to simulate the behavior of other flexibility assets like bidirectional thermal storage, building thermal management, and renewable sources. Additionally, the RTDS system behaves as a communication hub with other storage devices which are installed in different universities in the UK. So this was developed in an EPSRC project manifest. So it communicates with storage devices placed in Newcastle, Oxford, and Sheffield. Why do we develop this system? In order to study the optimal performances of storage units by means of a centralized controller, which was developed in MATLAB Simulink and speaks with the RTDS network simulator. The idea is that the provision of multiple services to power system is a smart way in order to increase the profitability of storage devices. In particular, we analyzed the provision of energy arbitrage and frequency regulation together. To do this, we developed a hierarchical control architecture, which consists of a day-ahead scheduler, a real-time MPC controller, which runs in MATLAB and speaks with the RTDS network simulator, and some local controllers, which are directly interfaced to the hardware and simulated units inside the system. Here, on the right side of the slide, we can see some profiles associated to the day-ahead behavior of the system in terms of storage units, state of charge, and the expected profiles for the energy arbitrage and for the frequency regulation. And we can see how these profiles change whenever we go to real-time condition. So the key, let's say,
And I think we've lost Alberto again. Is that just me? No, unfortunately, I'm seeing a few nods.
No.
Okay, well, unfortunately, we'll move on to the next talk. It seems like Alberto's having some connectivity issues. So we'll move on to the next talk, which is...
frequency regulation.
Ah, wait, he's back. Alberto, we've got you back again. Can you hear me? No? Okay, well, let's move on because this will become infuriating. Iñaki, do you want to take over? I think you're next.
Okay. Hello, everyone. Let's start sharing this. Share. Right. Okay.
Perfect.
Yeah, good. Yeah, the project that I'm gonna talk today about is the control of a wind diesel microgrid. First, the motivations, basically reduction of CO2 emissions, and basically addressing energy poverty in remote regions everywhere in the world, basically. And on top of this, increase wind turbine penetration in current systems, basically systems that are currently using diesel engine technology. The specific objectives is basically to generate simulation models to analyze the behavior of the microgrid. Then the construction of a hardware in the loop system, basically a laboratory platform to emulate what we mean by prime movers is a wind turbine and the diesel engine in the microgrid. And the implementation of control algorithms for different tests of the system. This is basically the experiment setup. As you can see, we have the two prime movers, the diesel engine and the wind turbine. Both of them are basically induction machines in reality, but we have some algorithms to represent the real systems. We have a physical gearbox, and the two generators that we are dealing with is the synchronous generator, one field synchronous generator, and a double head induction generator with some power electronics and resistive loads. We have a set of contactors to change the different configurations in the system. As you can see from this diagram, very quickly, not going into very much detail, we have a synchronous generator on your right, at the edge, and we have some regulation of voltage, frequency, and power, basically, in the system when they are connected together, or when the wind turbine is connected in standalone, which is something that can happen still. For the primary emulation, basically, we have speed controller in the systems, basically a governor or to control the speed of the wind turbine. G2 is basically what it could be a lookup table. G3 is an emulated inertia, and G4 is the drive that we use to run the machines with. With this, we have the wind turbine setup, which is basically done in D-space, connected to the induction machine and the generator. And this is our lab setup. On the other scenario, we have the diesel engine, and here is in the lab. So we need to evaluate basically the emulation effects. This is how it looks normally, the drive, when you put a 9 kilowatt load in the system. But when you start doing the emulation, you start seeing changes in the frequency. Obviously, we had to do some simulation before that, which is the red line, to predict what we will be seeing in the lab first. For the wind turbine, basically you have what you're seeing is a lookup table that we were using, where you have different speed conditions and power conditions. Basically, lambda is basically a relative speed between the wind turbine and the wind, and CP is how much power in rough terms you're getting from the wind turbine. We created an algorithm to select the speed, because in certain conditions, even if we wanted to operate in certain region, it is not possible because it will be overspeed or underspeed for the wind turbine. With this, we could get a full set of results for the microgrid connection, basically, where we have the emulated wind speed with a variable wind speed, the rotor speed changing with the wind speed. Something that I should have said before, sorry, is that we are using a variable pitch wind turbine. That's why we have in the corner beta angle, which is the angle of attack of the wind turbine. And we have basically the power that we extract from both from the wind and the compensation power that we get from the diesel generator. On the same scenario, well, different scenario, sorry, we have a standalone wind turbine here, where the turbine is providing some of the power by isolating the stator of the machine and providing some power isolated from the diesel engine. Of course, since we're emulating a diesel engine, we need to know what is the fuel consumption of the system, and what will be the impact of different load steps in the consumption of the fuel. And with this, okay, what do you do when you have the two systems? You need a criteria to say, okay, how are you going to use the wind turbine and the diesel engine? How you need to switch them on and off. From the literature review, basically, we could obtain, and from the system that we are emulating, some criteria for the operation on and off of the diesel engine. The conclusion is that we could get a fully validated simulation with the platform. The laboratory results showed a smooth synchronization, something very important. The wind turbine was verified both in simulation and experimental testing. And this allows for future integration of other power sources or power electronics. We could see a lot of potential for developing power electronics for the platform. So some references if you feel curious about this.
Thanks.
So, yeah.
Thanks very much. That was a bold number of slides to try and get through in 5 minutes.
Yeah.
There is a question for you, but I'm going to let you take that in the chat just because we're already running a little bit behind time.
Yeah,
So
thank you
very much for your presentation, and we'll move on to Anna who is going to be talking to us about wave energy converters.
Yes.
So you should be able to share the screen. Perfect.
Okay. Hi, good morning. My name is Ana Garcia Teruel, and amongst others, I do research on design optimization of wave energy converters. So why wave energy? There's a high energy potential available in ocean waves. The usable wave energy resource has been estimated to be 52 gigawatts in the UK, 300 in Europe, and around 3,000, globally. And to use this extensive resource, wave energy converters have been studied and developed for many years. To date, the levelized cost of energy of these technologies is around 100 to 500 euros per megawatt hour, but the cost is expected to reduce to 75 to 100 euros per megawatt hour after deployment of 10 gigawatts. For context, the LCOE of offshore wind today is around 100 euros per megawatt hour. So these are some examples of wave energy converter concepts that have been developed and tested, and they use different principles to extract energy from the waves. But the main components of a wave energy converter are the floating body, the power takeoff system that can convert the oscillation into electricity, and the mooring line that keeps the wave energy converter in place. In a simplified way, to extract more energy from the waves, the natural frequency of the floating body needs to match the frequency of the incoming waves, since then the body will have larger oscillations. The natural frequency of the floating body will depend on its shape. At the same time, there will not be only one wave of one frequency, but many waves of different frequencies. The floating body will be subject to high loads in high energetic seas, such as after a storm, and it should be easy to manufacture to reduce costs. So it is not trivial how to design the floating body of a wave energy converter. So to describe the main challenge here, we have two sides. On one hand, as you could see, there's a wide range of wave energy converter designs, and this points to the need of early stage design tools to explore more of the design space and avoid expensive design iterations later on once the device has been built. And on the other hand, the highest cost reduction potential is associated with the structure, and as you could see, it's not straightforward how to design the structure or the floating body, and for this reason many geometry optimization studies have been performed in the past decade, but there's no consistent methodology to do this. So if we bring those two together, we see that there's a need for wave energy converter geometry optimization tools that are able to generate improved early stage wave energy converter designs as with lower costs associated to the structure. And so for this purpose, I developed a wave energy converter design optimization approach capable of generating very diverse shapes so that we can explore more of the design space. And this is based on a previous method developed by the late Dr. McCabe and uses cubic B-spline surfaces to define the shape. However, as you can see from the resulting shapes from the previous study, the resulting shapes might not be able to survive high energetic seas or be cost effective to manufacture. So during my PhD, I expanded this method so that although being able to generate diverse shapes, the resulting shapes would have characteristics that truly reduce the LCOE. And this is not only maximizing power, but using different proxies for costs and accounting for a number of factors that will have an effect on costs, such as manufacturability. And so why is the world a better place? Why is this useful? So this is useful for technology developers who can apply the method to generate improved initial designs of their WECs or wave energy converters and avoid more expensive design iterations later on. And I am currently working with a technology developer to improve their design. And this is also useful for funding bodies who can use the metrics that I developed for comparison of the different designs to compare devices. And they can use the method to find potential limits of devices in terms of the optimal relationships between power, volume, and surface area. And I'm currently working with Wave Energy Scotland to define these types of relationships. So I am now a research associate in the Policy and Innovation Group at the University of Edinburgh. So if you have any questions or you're interested to know more about the work that we do, don't hesitate to get in touch. Thank you very much.
Thank you very much. Really nice presentation. There's a question from Richard, and I'm very intrigued as to how you embed some of those kind of constraints into your optimization around kind of, I guess, around like structural integrity of it. But I feel like that's a conversation that's not going to be dealt with in 30 seconds. Again, I'll let you answer Richard's question in the chat, if that's all right, just because in the interest of time, we want to make sure we can get through the rest of our presentations. But thank you very much. Really interesting.
Thank you.
So next up, we have Nathan Skillen. I see you've turned your video on. That's great. And you're unmuted. So if you'd like to share your screen and take over, it's over to you.
Hopefully you should be able to see that.
Yep, it's just coming up now.
Okay, thanks very much. So my name is Nathan. I work for the Bioenergy Hub. I'm sort of between Queen's University, Belfast, and Manchester, and all our work is really around photocatalysis and bioenergy. It's a relatively new field, which is why the title of my presentation is Finding Its Feet or A Step Too Far. So what I'll try and do in 5 minutes is give you a quick overview and a bit of a snapshot of some of the data that we've got. Now, I'm aware that not everyone will be familiar with photocatalysis, so I thought I'd start with a brief description about what it really is. And essentially, it's the same as any other catalytic process, apart from we use light to activate the catalyst. So usually you want to activate your catalyst to drive your reaction in some ways. So we don't use temperature or pressure, but we use light. And depending on the catalyst, you use different types of light. So what happens is we get two things. We get oxidation, usually using water, and we also get a reduction reaction. And in a really sort of brief nutshell, that's photocatalysis. That's photocatalysis in a nice little box. The main things are we get these radicals produced. So you see an OH dot and an O2 dot minus here as well. And it's what we do with those radicals for biomass conversion. So the way we apply it here is we look at radical attack of different types of biomass. And really what we're trying to do is break down some of the key bonding patterns within different types of biomass and release viable compounds or release energy as well. So there's a lot of interest in photocatalysis from that perspective. But where it gains a lot more interest, and where you see in the literature quite a lot, is the alternative reduction reaction that can take place, and that's hydrogen production. So if you modify your conditions slightly and you add a co-catalyst, you can actually generate hydrogen. So as a package, as a nice little neat box, you can see that we can potentially use solar light to produce hydrogen from potentially waste products as well. Now that's all really good, but at the end of the day, photocatalysis is quite a young field. The timeline here gives you an idea of it. And especially for biomass conversion, we're still an infant, I guess. We've still got a little bit of development to go, which means we're a little bit further down the TRL scale than other technologies. And the first paper was actually in the 80s, but it wasn't really until about 6-7 years ago we started seeing some more of the fundamental work. And then in the last couple of years, there's been a big increase in the number of papers that have been published on the topic. So you can see the two projects that we've had by the flags here. We started in about 2013. With the Bioenergy Hub, and now we're on to our second project with them that's just been running for, I think, about 6 months now. And what we're really trying to do is take the knowledge that we've got so far and push it a little bit further forward and advance the field if we can. So if I give you a snapshot of the data, we can do it as a reduction and oxidation. Now on the reduction, it's basically hydrogen production. And the good thing is we can actually get hydrogen from cellulose. And the chemistry is quite challenging there. So to get that to work initially, was quite exciting. And we can see that we can actually get quite a lot of hydrogen from glucose as well, which gives us an indication of maybe what the mechanism might be. So we've also looked at how we can enhance the amount of hydrogen that we get. So we use pre-treatment steps. That can involve some chemistry in terms of changing the structure of the starting material or even ball mill on it. And in both cases, you can see we get a nice increase in hydrogen, a nice increase in quantum yield. The other nice thing we can do as well is we can actually do solar activated photocatalysis. So the graph up on the top right here shows data for solar hydrogen production from cellulose. And this is work that we did at the University of St Andrews. Anyone who's familiar with Scotland will probably be aware that you got a better chance of getting windburn than sunburn north of the border. So to get solar hydrogen from cellulose is actually quite impressive, and we're really pleased with it. Now the other side of that coin is oxidation, and this is where it's a little bit trickier. Hydrogen production is relatively easy by comparison, but when we start looking at the oxidation and we start looking at the liquid phase products, the mechanism changes quite a lot, and there's an awful lot that goes on, and this is something that we're trying to figure out within our project. So if I use this graph as an example, we tend to see 20 to 30 different liquid phase products depending on what the start material is. Concentration range there is fairly accurate for an average reaction. Generally, lower concentration, we'll see sugars that we can use for bioethanol production, and then the higher concentration liquid phase stuff are usually smaller organic compounds. And a lot of them are actually viewed as potential platform chemicals, but it changes and it varies quite a lot depending on what that start material is. So depending on whether we're using just a standard cellulose, if we're using lignin, or we're using some sort of waste. The nice thing is though, that we can do it simultaneously. So this graph here shows some of the data that we can get, and these are sugars that we can get while we're also generating hydrogen. So oxidation and reduction reactions have to kind of happen at the same time. So we do have a bit of a dual purpose system. So not only are we generating valuable compounds in the liquid, we're generating an energy source from the reduction as well. And that's really it. That's photocatalysis and biomass conversion essentially in as quick a time as possible. So we've still got a little bit of development to go, but there's really desirable characteristics there which we're trying to push forward. So we'd argue that photocatalysis is now finding its feet in bioenergy. And our project going forward is really looking at controlling the mechanism as much as possible and investigating how we can develop it in terms of energy efficient systems and hopefully pushing towards sort of scale up and potentially a pilot scale deployment. Until then, I think at least we have some fairly pretty pictures that we can take of our research. Other than that, that's me. So thank you very much. If you have any questions, I'll try my best to answer them.
Thank you very much. I was going to say, it definitely feels like you're falling down on the finding its feet side of things, and seems very promising, even if it is bringing back bad memories of chemistry lessons for me.
Yeah,
I can't see any questions at the moment, but there might be some that pop up. And again, in the interest of time, I'm aware we're already running a little bit late. So let's move on to Hung-Yin Lin, who's going to be giving us a presentation on sensing with terahertz waves with respect to energy storage. So over to you.
Okay, so you guys can hear me, right? Yep, okay. So yeah, hi everyone, my name is Hung-Yin Lin, and I'm currently a lecturer in electronic engineering in the engineering department at Lancaster University. So it's been very interesting to hear all the different talks so far, but what I'll present now is how a relatively untapped portion on the electromagnetic spectrum, that is terahertz, could also be useful for characterizing materials, unveiling interesting material insights, which could be applicable for energy storage materials and devices. And I'll show you an example on how terahertz could be used for looking at hydration, building up inside hydrogen-based fuel cells, as an example. Okay, so what you see in this slide is basically where terahertz sits in relations to other portions of the spectrum. So terahertz is situated between your low frequency microwaves and a higher frequency infrared. Now, traditionally, terahertz has actually been difficult to tap into due to a lack of sources and detectors. But the technology has evolved now that we are able to tap into this portion of the radiation quite easily using commercially available benchtop kits that you see down here. Now, what makes terahertz interesting for material scientists and also engineers is some of the key characteristics it has to offer. So for example, it's able to penetrate through materials that are otherwise opaque at optical frequencies. So materials such as polymers, semiconductors, and ceramics. So by exploiting short pulses of terahertz that we can generate, we can then start resolving their internal structures. In this frequency band, it's also sensitive to fundamental physical processes such as intermolecular hydrogen bonds, phonon modes, etc. And whereby terahertz radiation is strongly absorbed, leading to sharp resonances. And this is important if you want to identify different chemicals, etc. So chemical fingerprinting. So it's the combined ability of seeing through things and recognizing different chemicals that makes terahertz rather interesting. And finally, you probably be thinking amongst yourself, is this radiation dangerous? So terahertz is generally classified as low frequency radiation, so it's not ionizing to your samples of interest at all. So using some of these key characteristics of terahertz, a lot of industrial applications have sort of gradually opened up. And so what I present now is an overview of some of those applications. So the first of which is in terms of analyzing film coatings in pharmaceutical tablets. And so in particular, what we are interested in here is measuring the film coatings of the tablets that we take, the pharmaceutical tablets. So the measurement principle here is really based on the fact that for every change in refractive index or change in material that light encounters, you will produce reflections. So if you look at this little diagram here, at this air coating interface, you produce the first peak, and similarly with this coating core interface. So if you look at the time lapse between successive reflections and you know how much light is slowed down inside the material, that is the refractive index, you can effectively determine what the coating thickness is. Now, as each of these pulses, terahertz pulses, is in the order of picoseconds, so that's 10 to the minus 12, you can ultimately resolve coatings down to 30 to 40 microns and get a spatial resolution about 200 microns. But that's just single spot measurement. You can then start to raster scan through the entire tablet using this custom built system, and then you can form nice images of the coating profile of individual tablets. So it's very good that we can, image individual tablets, but what's more important for the pharmaceutical manufacturing industry is the process monitoring and the eventual process understanding. So the bulk of that work here is really try to scale down the coding process to a lab-based environment so that we can start collectively studying it with terahertz sensor. And then here we are also combining with some optical sensor. And the reason for combining it is because we can then start looking at very thin coatings. And what we want to do there is to combine these different measurements into a numerical process model that is very much designed to capture the process complexities. So this is still very much a work in progress. Now, using other characteristics of terahertz, we can also look at stuff like mapping out the electrical conductivity of graphene over large areas. And so the conventional way of doing this is, if you've got a sheet of graphene, and how do you measure the electrical conductivity, is you need to make electrical devices by means of lithography. Now, as you guys may or may not know, this is a very time-wasting and a destructive method. Because once you make the devices, you then need to measure each of these devices individually, and then you throw away the wafer. So what terahertz spectroscopy has shown to do is you can measure the electrical conductivity of graphene non-destructively, so you don't need to make any of these devices, relatively fast, so in the order of milliseconds per point, and also no physical contact because it's light ultimately. Okay, so having looked at some of these examples on what terahertz could do, we could also use terahertz to start looking at water content inside materials without physical contact. And so my PhD student, Desio here, basically he has put together a simple terahertz transmission system, right? So you've got some sort of a terahertz source, some sort of terahertz camera, and you've got some sort of sample. So it's a transmission setup. Now, liquid water, we know that it's a material that is very polar and so strongly absorbs terahertz. So if we put a detector after a liquid water, what we would expect is that there will not be much terahertz transmitted because it's all absorbed. And that's what we see in this little diagram here, as opposed to when the sample holder is filled with air, for example, so free space, whereby all the terahertz will just transmit through and we get this lovely yellow spot. So it's good that we can qualitatively see this, but what's probably more exciting is if we can start quantify the amount of water there is, okay, and from a light measurement. And so what we did was then we started playing around with different water thickness, and this corresponds to these dot points, and this is plotted against a backdrop of Beer-Lambert's law. Okay, and so what this means is that from a relative terahertz measurement, you can start estimating the water thickness. And so we applied this to Nafion membranes, which, if you don't know, it's a membrane that is commonly used in hydrogen-based fuel cells. And we want to see the sort of water pickup there. And what we did there was, with a Nafion membrane, we basically watched the water dry from the estimate. So from the relative transmission, we can then estimate the water thickness, and from the water thickness, we can then estimate the water. content. And this is sort of benchmarked against a simultaneous gravimetric analysis, whereby generally there's a good agreement between the two. Now, because we're using a terahertz camera, right, ultimately we can then start doing images. And so this is what we...
Sorry, just to jump in, just in the interest of time, are you getting near the end? Just because you...
Yeah.
I just want to check, we're going to have to wrap it up soon because we've still got another talk to get through.
Yeah, sure. So this terahertz images just basically shows areas of dryness versus areas of wetness. And what you can see is over time, you get replaced with areas of dryness. Okay, and obviously now what we're doing is we're extending this further to an actual hydrogen-based fuel cell in operation, and whereby what we can start seeing is the buildup of water in water channels. So this is the very beginning of a process and very end. So this is, again, a very early work in progress. Key summary. So you've seen some of the key characteristics of terahertz and examples of applications for, say, looking at structure information in pharmaceutical film coatings or functional information in terms of electrical conductivity and also the water content. So obviously I have to thank to my funders as well as collaborators, and yeah, any questions?
Brilliant, thanks very much. Very interesting talk. Looks like there's all sorts of interesting applications for that. We'll take questions for that in the chat window if there are any, because I'm aware we're already, unfortunately, over time and still got one interesting presentation left to go. So Kezia, over to you.
Thank you. Can you see my presentation all right?
Yes, I do.
Brilliant. Thank you for the opportunity and for all the 70 people who still stayed back to listen to the last talk. I'm Kezia from the University of Sheffield. I'm a final year PhD student, and the title of my research is Metal Organic Nanosheets, a New Dimension in Organic Photovoltaics. So metal organic materials are a class of supramolecular materials where we have an organic linker and a metal ion cluster that are coordinated together to form extended three-dimensional network structures, and they've been found to have application in the field of sensing, gas separation, drug delivery, and gas storage. They had a brief time of being tested in dye-sensitized solar cells, where they were used to have a systematic arrangement of the dye molecule in order to reduce recombination losses. But their 3D structure makes them limited for applications in thin film solar cell technologies. So in our group, what we focus on is taking a layered morph structure and exfoliating it into nanosheets. So what we do here is we are then exposing the surface area of these materials by having them in nanoscopic dimension, and this also enables them to be easily blended with fullerenes and polymers, and thereby provide easy integration into thin film solar cells. So looking at, in my project, we started off by testing porphyrin-based structures, which are synthetic analogs of chlorophyll and make sense when one of the applications is light absorption. So this is how the material is made. So since these materials have a modular structure, you can tune the functionality by choosing the organic linker of choice for the particular application. So here we have the porphyrin system that is linked with the metal cluster to form the 3D morph structure, which is then exfoliated to form the nanosheets that are known as MONs. And microscopic investigations show that these materials approach monolayer thickness and are about 100 to 500 nanometers in lateral dimension. So why MONs? These are an emerging class of 2D materials, and what sets them apart from other 2D materials like graphene and transition metal dichalcogenides is that their band gap is structurally tunable, not layer dependent. So the band gap arises from the organic linker that is being used to form these structures. They are also far more easily solution processable, approach monolayer thickness, and can be easily scaled and are also stable at room temperature. So harnessing these benefits of MONs, these porphyrin MONs were then investigated in a ternary system with P3HT-PCBM, mainly motivated by the ideal position of their band gap with the donor and acceptor in the system. And after optimization, we found that about 20% by weight of these MONs in the ternary system contributes to a near doubling of device power conversion efficiency with simultaneous improvement in JSC, VOC, and FF. And a careful look at the EQE spectra shows that there's enhanced absorption from the contribution of the porphyrin groups in the MONS system, and also a higher percentage of crystalline P3HT in the system. We did further analysis and came to the conclusion that MONS act as templates for improved crystallinity of the polymer, which is supported by the calculation of grain sizes from AFM investigation and also from the GWAX data and the absorption spectra, where we observe a decrease in the amorphous P3HT region. So, and currently we're investigating the energy level alignment of these systems in the ternary blend to see what role the importance of energy levels plays in contributing to an enhanced performance without creating traps for the excitons. So to conclude, this work kind of sets the stage for investigation of low dimensional materials in organic photovoltaics. So mainly that having the right morphology and the right energy levels can create new possibilities for integrating these systems into thin film solar cell technologies. There is a wide scope for investigating other materials by replacing the metal units and the linker and kind of studying an entire library of these compounds and seeing what kind of an effect they can have in the solar cell system. With this, I'd like to conclude my talk with a big thank you to all my collaborators from EPMM Sheffield, Foster Group Sheffield, and Helmholtz Zentrum Berlin. And thank you to all the funders. I'd be happy to take any questions.
Brilliant. Thank you so much for your talk. So I just want to check. So this is for like organic solar cells, did you say? And so what kind of, where are they? So I'm completely oblivious to anything to do with organic solar cells. How far away are we from having them as a kind of competitive product?
So you mean with these materials in organic solar cells?
Yeah.
Or in OPV as a technology in general. So the highest performing OPVs are about 15% right now with different device configurations. So the different systems that we've investigated using MONS, obviously I presented the first example that we tried. So where we are currently is about 12%, which is yet to be published. But yeah, still a bit more long way in establishing these materials as, you know,
but like you say, there's a huge library of potential combinations that you've got there, and maybe some of those might prove to be a bit more
correct. Yeah,
a bit more valuable.
There's a huge opportunity to investigate different things, and yeah, it's just the starting where we are right now.
Excellent. Brilliant. So thank you so much. That's our last talk. So one thing I want to do, and hopefully I'm sure you're all doing it at your end, is a big thank you to all of the speakers that we have. There's no easy way to do this in an online way. There is some kind of online reaction you can clap, but I'm assuming you're all clapping at home. So thank you very much to all of our speakers. It's been really interesting for me to see the breadth of work that's going on across all of these different hubs.